So in this video, we're going to talk about the acid dissociation constant, all right? Or in other words, the acid dissociation, can't say that word today. All right, the acid dissociation constant, all right? Other words, we just note it at Ka, all right? Or K sub A. Now, if you recall, K is basically an equilibrium constant where when we're talking about in terms of equilibrium, it's the concentration of your products divided by the concentration of reactants. Well, when it comes to acid dissociation constant, it kind of works the same way, all right? And so if you have, like, for example, so because we're talking about a acid dissociation constant. So if you were to have a weak acid, so HA, right? H is the hydrogen, A will be the conjugate. Weak acid plus, let's just go with water, right? And so because it's weak, it's going to be at equilibrium. So weak acid plus water, all right, and what you're going to form is hydronium ion plus the conjugate, all right? So let me go ahead and let's label this. So here we have the weak acid. This is the hydrogen for the weak acid, right? And this is the conjugate base, right? And so if you were to consider writing the equilibrium expression for this, right? It'll be K equals, now remember, these are both aqueous solutions, all right? And so that's your product. So I'm going to write this on top, divided by, and then here's your acid. Your acid's typically aqueous. Water is a liquid, so we always leave this out. So HA. So when you're looking at the equilibrium of a weak acid, instead of calling K, we call this Ka. All right, so the acid dissociation constant. All right, which is a lot like the equilibrium expressions that we've talked about in previous videos. All right, and the way you interpret Ka is the same way you would interpret equilibrium, K, just a regular equilibrium constant. And so, like, for example, if we were talking about like a strong acid, right? And like we said before, strong acids, they dissociate completely, right? And so if you were to think about this and say, like, let's say, for example, this equation I drew here was a strong acid. Well, then it will go completely this way, right? And if it completely goes completely in completion, this way, you will have nothing but product. Then what we say that here, then this is going to be highly product heavy. If it's highly product heavy, the Kas will be very large, much larger than 1. And oftentimes, it's so large, it's really, really hard to actually truly measure this in terms of Kas, all right, and so it's really it's not useful to us, but essentially that's what the case is. Strong acids have large Ka values, or great, that's much larger than 1 because it completely dissociates, right? It's favored, its product very, very highly product favored. Okay, now weak acids and typically will exist in equilibrium, and depending how weak the acids are depends on the strength of the conjugate base, all right? And so you may have that, and not may have, but typically what we find is that weak acids have Ka values that are less than 1, all right? So strong acids have Ka values that are greater than 1, actually much greater than 1, while you have weak acids, their K values are less than 1, all right? And the weaker the acid, the smaller that number, okay? And remember, we talked about this in the previous video that, there is a relationship between the the weakness, or actually the strength of the acid compared to the strength of its conjugate base. And so the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. All right. And so we could use Ka values to basically determine the strength of an acid or not. All right. Another thing that it's important to know is that donation of each successful H plus or hydrogen ions from a polyproptic acid is more difficult than the one that came before it. So polyproptic are just basically acids that have multiple hydrogens. So just like H2SO4 or H3PO4, these are polyproptic. All right, because it contains multiple H's. All right, versus your monoprotic, like your HCl or HClO4. Okay, and so as I said earlier, the donation of each successful hydrogen from a polyproptic is more difficult than the one before it. So that simply means that when it loses a hydrogen, the Ka values are much lower. So the acid becomes even weaker. All right. And so let me kind of give you an example of this. When we have H2SO4, all right, thank you. So we have H2SO4. If you consider its Ka, right? This Ka here is a very large number. All right. It's greater than 1. All right. Because H2SO4 is a strong acid. But once it loses the H to become hydrogen sulfate, right? HSO4, then the Ka value is 1.2 times 10 to the negative 2. All right, so this tells you that it is reactant heavy, and so because it's reactant heavy, or the Ka is less than 1, then we know that this is a weak acid. Now, we see this trend even more with phosphoric acid, because H3PO4 is not a strong acid at all. So when you have H3PO4 and we consider its Ka, it is 7.5 times 10 to the negative 3. That's the Ka value. Well, if it loses a hydrogen to become H2PO4 negative, the Ka value is 6.2 times 10 to the negative 8. So you see the Ka actually decreased, so it became a much weaker acid. All right. And if it loses one more hydrogen to become HPO4 2 negative, then the Ka value is 2.2 times 10 to the negative 13. It's even lower. Okay. And so this is what I mean by when you were dealing with a polyprotic, the donation of each successful hydrogen ion is going to be more difficult than the one before it. All right. And so this one was relatively not that bad. All right, but to get rid of the second hydrogen, it takes a little bit more, right? The Ka is much lower, so that particular substance actually want to hold on to this hydrogen a little bit more. It's not as readily ready to give it up. And if you manage to lose that hydrogen, well, that third one's going to be quite the beast for this substance to release. All right, and so that's how you're able to tell. Now, when we're looking at this, right, and if you consider the strength of the conjugate base, right, H of these three, if you were to rank them, right, the conjugate base for H3PO4 will be the weakest, all right, because of all of these three, it's the strongest of the weak bases, if that makes sense. While the conjugate base of HPO4, right here, will be the strongest because it's the weakest weak acid. All right, if that makes sense. So that's the way that you could use Ka values so that you could kind of relate, or you're able to determine the overall relative strengths of different weak acids and strong acids as well.